We're going to spend an hour talking about shock tubes, techniques, applications, the latest versions of how you do shock tube experiments. Why? Shock tubes are a very convenient way to generate a very well-known sample of high temperature gas. And you'd like to study perhaps the chemistry that takes place in that sample by measuring the species evolution with time, for example, using laser absorption. So it's like laser absorption and shock tubes are made for each other. So there's lots of applications of laser diagnostics to practical combustion systems, but research, in terms of research, a shock tube is a very convenient way to generate known samples of gas that can undergo chemical reaction, or we study them spectroscopically. We use them a lot of different ways. We've got 5 shock tubes at Stanford. So we're going to talk about shock tubes. I'm going to give you as a kind of a different example how we can use them to study vibrational relaxation as well as chemistry. I'll talk about how we use them in the simplest way you can use them is to study ignition time delays. And then I'm talking about the very latest thinking about how you model a shock tube experiment. Because even as good as they are, there are issues that you have to avoid or deal with. And these would be examples of 1 or 2 different shock tubes at Stanford. So, a shock tube usually is a constant area tube about 100 diameters in length, separated into 2 chambers by something like a diaphragm or a rapid opening valve, separating the driver, which is the high pressure gas, from the low pressure section, which is the test gas. Usually this is called the driver, this is the driven section. This one typically much longer. They're usually constant area, and the overall length is about 100 diameters. When this diaphragm breaks due to pressure, usually, it takes about 5 diameters for a wave to form into something that looks like a planar wave. It then moves at nearly a constant speed, not a constant speed. Ideally, it's a constant speed. And then gradually it slows down a little bit, maybe 1% per meter near the end. And we will perform an experiment down near the end, usually. That's called, and that's an experiment we would conduct behind the reflected shock wave. So what happens is that we pressurize, you fill this section with what you're interested in studying, you pressurize this until this diaphragm breaks. It might be thin, it might be thick. We vary that in order to change the pressure ratio. Pressure ratio for fixed gas composition dictates the speed of this wave. The wave moves down at more or less constant speed and then reflects and leaves behind a stagnated sample. So in an ideal world, when this shock wave reflects, the boundary condition is velocity of 0, and that condition applies everywhere in this red region. It's not an ideal world, but it's close. So we work kind of close to the wall, 1 or 2 centimeters away, where it's basically stagnant, and it's at a known temperature. How do we get the temperature? We measure the speed. From the speed, we can get the temperature to within a fraction of a percent. So it's a pretty amazing way to get a known sample of gas. The diameter of this tube might vary. We have diameters that vary from 2 to 15 centimeters. 2 to 15 centimeters. I didn't say that right. 2 inches to 15 centimeters. So 5 centimeters to 15 are the diameters that we have. The shock wave is very thin, and so basically it's a step change in temperature. Shock wave is actually a few mean-free pads thick, but that's negligible for us. So it's basically a step change in temperature and pressure for this gas, causing it to begin to change. It could be, how does it change? Temperature changes. That means the rotational temperature has to change, the vibrational temperature has to change. Then the chemistry takes place, and temperature may change. So usually there's 1 temperature, but I'm going to show you an example where there's 2. As far as I know, the first application of shock tubes was around 1899 in France by Paul Vier. There was a lot of interest in the Second World War period in using tubes to look at mine safety and explosions and aerodynamics. In the 50s, as far as I know, that was the first time it was ever used to study chemical kinetics. I thought it was at Caltech. Somebody tells me it might have been done at Toronto. It was about 1953, 1954 that people realized that you could use the step change in temperature to trigger a chemical reaction and watch it evolve. So whoever did it, it was about that time. That was a time when the Second World War led to a lot of technical advances, the development of infrared detectors. Lots of detectors were developed in that period that we need, because these experiments, you have to have time-resolved measurements. There was a lot of interest in the 60s in re-entry studies. So they worried about planetary entry and very high velocities. How do you produce in the laboratory things that simulate the conditions for, say, entry into Jupiter? So this was a way to generate, for short times, very extreme conditions. And there are a lot of different designs. The shock tube design I'm talking about is called pressure-driven. It's the simplest, cheapest, safest. But I've been around shock tubes that are driven by electrical discharges that would rock the building when the discharge goes off. So they use different strategies. But combustion, the temperatures aren't that much, 1,500 degrees, 2,000 degrees. They were worried about 50,000 degrees or some extreme conditions. I think it was 1970 when lasers were first used to measure species in the shock tube. That would have been one of my friends and me. And so it's evolved, and it's continuously evolved. So lasers were invented in 1960. They started getting kind of out of we know how to make a laser mode into the 70s. People got interested in beginning to use them for science at about that time. You can use these to study, say, spectroscopy. Maybe you're interested in fact, one of the people that I know was interested in the spectroscopy of comets. You might be interested in looking at blast waves. So aerodynamics, chemical kinetics, heat transfer. There's a lot of reasons why you might like to have these high temperature flows. Now, high temperature is high enthalpy, so you also can have a nozzle in the end and expand that high enthalpy gas out into a hypersonic shock tunnel, and that's how really high Mach number flows are created in the laboratory using shock waves. The theory, maybe you've seen this, probably you've seen this. If there's a moving shock wave, and you know the conditions upstream, you can solve for the conditions in the shock. You can solve for the conditions everywhere, across the wave or even in the driver gas. You can calculate kind of everything with standard relations. You have to say something about gamma. You have to know the composition, but then you can calculate everything. So you can also calculate what happens behind this reflected wave. If you measure the speed coming in, you can calculate the conditions here quite accurately. Here's just some examples. So let's say we have gamma of 7/5 gas. If we have a 6.6 Mach number wave, pressure jump is 50 across the incident wave, another factor of 7, so 350 across the reflected shock wave, and factor of about 10 in temperature. That means it's around 5,800 degrees, and then another factor of 2 across the reflected wave. So you can quickly generate really high temperature gases, much higher than we need for combustion. Combustion, we're down here at low Mach number, well within the regime. You want a stronger Mach number, what do? You have higher pressure in your driver. The P4 over P1 ratio controls the speed for fixed composition. You want a stronger shock wave, you use helium in the driver. You want a yet stronger shock wave, you use hydrogen. So you play with the composition of the gases and the pressure ratio, and you can produce kind of anything you want. You have to think about a shock wave as a transient event. So here's the diaphragm. This is an XT diagram. This is X. Here's where the diaphragm is. Here's the end wall. This is time. The diaphragm breaks. The shock wave is formed, moves at ideally a constant speed, reflects and leaves behind this region 5. That's the test gas right there. However, there's this trailing contact surface that separates the original driver gas and the test gas that's coming along right here. And when this wave comes back and hits that interface, it may or may not send a wave back that terminates your test time. If you're clever, there's a way to nullify this and extend the test time so that it ends when this expansion wave here kind of eventually comes around and terminates things. It's easy to get a few milliseconds. You have to work to get tens of milliseconds. What have I got here? I've got a plot of test time. This is reflected shock. This is test time in microseconds. Okay, this is 1 millisecond right there. 1 millisecond. So it's easy to get a flat condition. Then if you haven't fixed this problem, you'll get some sort of a distortion. If you fix that problem, you can get 10 milliseconds pretty easily. And all this depends on the length of the shock tube. So you can just also make your shock tube longer if you have room. So if you fix this problem, it's called tailoring. I think it was first done in Europe, maybe around 1965, 1970. All it means is when this wave comes back and it's passing through this test gas, you have to arrange what's called the acoustic impedance of this gas to match the acoustic impedance of this gas, in which case this contact surface will go vertical and there is no wave reflection. Then you get longer test times. It's not perfect, but here's an example. So if we apply this, now all of a sudden we're getting, what, 9 or so milliseconds. It's not perfect. There's a little something going on here. But we can go from a millisecond or two out to 9 without too much trouble. And we found ways to go farther. I think we have achieved up to about 45 milliseconds when we did pull out all the stops. I don't think I have the plot, or maybe I do a little later. I'm going to show a plot that compares what you could do with the shock tube in a rapid compression machine. I'm going to take a detour because we've been talking a lot about spectroscopy and energy levels. I want to show you how we can use our laser absorption to study the process of vibration and relaxation. So here's our familiar diatomic, harmonic oscillator diatomic molecule. And here in the font that you can't read is basically G equals, you know, the energy expression from quantum mechanics. Here we are. Looks like I'm now using I instead of V for the quantum numbers. They're quantized. You can use Boltzmann statistics. I'm sorry, it's too small to read, but you now know what it is. This is the Boltzmann distribution in level I. What's the degeneracy of level 1? For vibration alone, the degeneracy is 1. Only when we introduce the rotational state that we pick up the 2J plus 1. Okay, so if you were to look at the, this would be the Boltzmann, the fractional population as a function of level I. So if you're at low temperatures, everything's at 1. This is the Boltzmann fraction. Sorry, it's missing. So they're all in level 1, and basically very, very little down here. But if you go to high temperatures, what happens is you begin to populate these other states. So there's always a straight line if it's a harmonic oscillator and it's the Boltzmann distribution. Well, what happens if you're at room temperature and you suddenly convert the translational temperature to, say, 2,000 degrees? What suddenly? Across the shock wave, which is 3 or 4 or 5 mean free paths thick, the molecules become randomized and have a kinetic energy associated with temperature, Maxwellian distribution of that, say, 3,000 degrees. More gradually, the rotational population evolves and it comes up and matches the translational temperature, maybe 10 collision times. So within a pretty short time, there's an established translational and rotational temperature, but the vibrational temperature lags. It takes time to provide populations in these higher levels because they're more demanding. You have to have a collision that brings in the vibrational quanta, and only a small fraction of the collisions have enough energy. So it takes a lot of collisions, depending on temperature, to populate the upper vibrational levels. And we're going to see this. Now, it turns out that some very smart people, at least one of them has a Nobel Prize, Teller and Beta and Teller, found that if you have a harmonic oscillator, equal spacings, and if you start with a Boltzmann distribution, you can show that the distribution function will evolve through a sequence of Boltzmann distributions. In other words, there will always be a vibrational temperature if there was one initially, but it changes from its initial value to its final value. And therefore, you don't have to invoke rate equations for every level. You can use what's called a relaxation equation. So in the case of vibrations or a harmonic oscillator, you can show that the vibrational energy per particle, or per unit volume, whatever, is simply the difference between the value that it would have at equilibrium for that translational temperature and the local value. So when this value goes to 0, it stops changing. Initially, it starts at the low value of room temperature, and meanwhile this gas is at 3,000. This would be the equilibrium value, divided by a characteristic time tau, which is a function of temperature and pressure. Because if you increase the pressure, the collision frequency goes up. So this equation governs the evolution of the vibrational energy, and I don't have to write a rate equation for every single reaction, which is effectively what Professor Pilling is talking about when he does his some of the things he was talking about in his lectures. Now, this equation for tau, this is a bit of physical chemistry here. This equation for tau is 1 over a quantity. Let's forget this one again. This is M is the total number density, Z is a collision frequency, and P is a probability that if you are a molecule in one and you have a collision with anything, you will go to 0. It's a very fundamental number per collision. So that's the only fundamental rate parameter in this problem. If you tell me this, and you tell me the density, number density of molecules, and this cross-section, which we'll take as constant, I can calculate the time. But it does depend on composition. So we're going to try to measure this. And this is what it should look like. If we have we're watching the shock wave go by, and we're down near the end of the shock tube, so we're sitting here, and here comes the incident shock wave, and it goes by. The translational temperature jumps up, then it comes down. Why does it come down? Because you're changing energy. So you have a conservation equation across the shock wave that says h plus 1/2 u squared is a constant. And so one temperature is going up, so the other one has to come down. So you're seeing the evolution of the vibrational temperature. Now the reflected shock comes by, and it happens again. So here's the vibrational relaxation process. So if we could measure T sub V, we could measure the relaxation time. And we're trying to do this now, as a matter of fact. So these are just the words that are in your notes. Now, some very capable guys back around 1960 who were interested in this problem. And they were interested in this problem because of this reentry business. People wanted to run facilities on the ground that involved high Mach number. They wanted to test at high Mach number. How do you get to high Mach number? You have to heat. And when you heat, gamma is no longer 7/5. It starts changing on you. And you have to start thinking about gamma and how things relax and how long it takes. Now this was at a time when they did not have lasers. So they used something called Mach-Zehnder interferometry, and here's the instant shock wave, and they measure fringes in interferometry. And this is this drifting of a change in the vertical direction of one of these fringes corresponds to a change in density. And so you can measure the change of anything, density, temperature, you can infer tau. And you typically plot this as p tau because tau is inverse with pressure, that's atmosphere seconds. And instead of 1 over k, which is what you use for kinetics, you use t to the minus 1/3 because the relaxation theory that was developed by a lot of famous applied physicists in those days said that it ought to scale with t to the minus 1/3. I won't go into details. Here's pure oxygen. So when you go to, the times to get down here, what is this, 10 to the minus 4 seconds. 10 to the minus 4 seconds when the temperatures are here at about 4,000 degrees. So why is it longer when you go to low temperatures like 500 degrees? Because the fraction of the collisions that have enough kinetic energy to make this happen diminishes to practically almost 0. So it's very strongly temperature dependent, T to the minus 1/3. And this is nitrogen and air, and this is pure nitrogen. So nitrogen is longer than oxygen. Why? Because the vibrational spacing is higher. It takes stronger collision. Nitrogen in air takes less time than pure nitrogen. Why? Because the oxygen wants to go first and it helps its neighbor. So it depends upon the mixture. There's a lot of scatter in these data, which are taken this way, and so we're just right now involved in what I believe is probably the first time that this has been done with lasers to try to measure this more accurately. And it's in conjunction with an effort by the Air Force to study re-entry at a more fundamental level. So we're going to study oxygen, pure oxygen and oxygen and argon, and we're going to use UV absorption in what's called the Schumann-Runge system. So now we're at UV wavelengths. That means it's an electronic transition. It's very famous, Schumann-Runge. That's responsible for the vacuum ultraviolet. So if the light is shorter than around 190 nanometers, it doesn't go through this room. You have to have a vacuum to propagate light shorter than around 190 nanometers. So we're going to work a little bit longer than that with a laser we call Mira that works in this wavelength range. And we're going to try to measure this. So now we have a pretty complicated, well, it's expensive. I wouldn't say it's complicated, but it's a very expensive laser. And we pass it through here, and we're going to measure as a function of time using Beer's law. only now we're going to think about number density, cross-section, and we're going to recognize, and path length. So they're missing an L there. There should be an L. But now it's a function of two temperatures, so I got to be a little careful. There are two temperatures in this problem. And I want to measure the evolving number density or vibrational energy using mirror. How does this relate to the vibrational population? So you can calculate with the principles that I'm telling you about. You can calculate the line strength or band strength versus frequency, wavelength, for each of the vibrational bands. Buried underneath these curves are all of the rotational transitions. So this is a simple way to plot the forest of lines that are associated with absorption transitions from V double prime of 7 to the allowed upper state. So, and this tells you that how it changes with V at a temperature of 2500. So at 2500, that's approximately the characteristic temperature for vibration of oxygen, about 2500. So anyway, we can tune across this region, and we can park our laser, and we can measure the absorption, which is what the student just did. He's in his first year. And he does an experiment at 211 nanometers, 15% oxygen, balanced argon, 1300 degrees Kelvin, 1 atmosphere, path length of 15 centimeters. This is the absorbance he measures. So he measures I over I0, takes the logarithm, and he plots absorbance versus time in microseconds. Absorbance is 0, here's the shock wave, and now it starts to go up. And absorbance goes up because the population in the absorbing state goes up. We're measuring the time evolution of the population in what is probably B double prime of 4 or so. Depends on the wavelength. Ideally, we could measure the population in V equals 3, 4, 5, 6, 7, 8 and test the hypothesis that it's in Boltzmann distribution. But all of our calculations show that it just stays in Boltzmann, so we can measure it at any wavelength we want. This is equivalent then to measuring vibrational energy versus time, and therefore it's equivalent to giving us the relaxation time that we want to plot on this diagram. And here are his data points. And oh, what I didn't tell you is those clever people back in the 60s who got that data did some correlations and took a best fit and came up with some expressions. Interestingly enough, we're awfully close. The difference is they have huge scatter in the data and we don't. That's the virtue of the laser. So in a sense, we're repeating an experiment that was done many years ago, 50 years ago, but we're doing it in a modern way with more precision. And the goal is to create a database that the modelers who are interested in what's called energy transfer, form of kinetics, can test their models. Basically, if two molecules collide, what's the probability of a vibrational transfer? And that's kind of what they try to calculate and test their models. So we're working on this right now. Now, that was a diversion because I thought it would tie in with the spectroscopy. The simplest way to use a shock tube for combustion is to measure the ignition time delay. That's like the simplest, crudest thing you can do. To help you understand that, let's look at the kinetics of branched chain reactions. This would be, sorry for this missing column, I think there's just numbers over here. This would be overlapped with Professor Pilling's lecture, and if anyone who's had a combustion course in combustion chemistry, you will have learned that why the H plus O2 reaction, here is called the branching reaction. So that's like one of the most fundamental things to learn. And the idea is that somehow you generate an H, and probably by this reaction. Turns out you don't actually care how you generate the H. Once you have an H, you set off a sequence of steps, 2, 3, 4, and they happen fast. And so the net result of one of these is this combination in which one H has been converted to 3. So one H gives you 3, 3H gives you 9, 9 gives you 27, and it explodes. And they call it a branch chain. So that's what happens, and that's why this reaction here, which is the so-called rate-limiting step, is so very important in much of chemistry. Therefore, it strongly influences the ignition delay time that we're going to measure. So this is how you would typically do this experiment. You would measure pressure, or you'd measure emission, for example, from OH. You would shock heat some mixture of hydrogen and oxygen, say, to 1100 Kelvin, 3 atmospheres. And what you would see at your sidewall location is you'd see the pressure jumps up when the incident shock wave goes by, pressure jumps again when the reflected shock wave goes by, and then about 170 microseconds later, pressure goes up when it ignites. So if you only want one number, what is the ignition delay time? That's how you can get it. You can also get it by looking at the emission of UV light, which occurs at the same time. Now, that's a common parameter. An engine designer wants to know the ignition delay time. In a scramjet, there may be approximately 1 millisecond to mix and burn the fuel. So engine designers care about ignition delay time as a design parameter. But this is kind of a crude number. It's kind of a crude thing, and there's some difficulties in measuring it accurately. So that's how it's usually done, by pressure or emission. You get pretty good agreement between these two methods. And so that leads to questions like, how does the ignition delay time vary for different alkanes? So if you had 4% oxygen and argon at 2 atmospheres, coolants ratio of 1, and you vary the alkanes from C4, that would be butane, up to C9, how does the ignition delay time vary in this regime between 1250 Kelvin and 1500? That's called the high temperature regime. So that's butane to no name. And what we can see by working at this carefully, the student worked hard at this, that you can see that as the hydrocarbon molecule becomes larger from C4 to C9, there's very slight reduction in the ignition delay time. Why? Well, equivalence ratio is 1, so now you have to understand this is fixed oxygen, so equivalence ratio of 1, you're putting in less fuel and the fuel gets bigger. So it's not just a question of how many hydrogen atoms there are. But the molecule gets a little bigger, it gets a little easier to produce that first H. A little easier to produce that first H. And therefore, you can see this. And the people doing theory really like this. They want to be able to show that they understand that they can model this very slight variation with size. But the interesting thing really is, how does this behave once you get into lower temperatures? And when it turns over, it goes like this, ignition delay time versus 1 over T. That's called the Ntc region, meaning that the negative temperature coefficient. So whether it goes negative or it goes flat, if it changes slope, you've changed the chemistry. Something different is happening. New reactions are taking place. And then what will happen is it'll go up again. These are the hardest experiments to do. There's a lot of scatter from laboratory to laboratory, and yet they're the ones that have the most interesting chemistry right now, people that don't yet understand. So we are working on this problem. And this has forced us to pay attention to exactly how our shock tube works and how do we make it work even better. And how do we get longer time so that we can go to lower temperatures. So we've come up with some schemes. This is an extended driver. We've come up with a scheme I'm going to show you here about how we've tried to make our test times more constant, more uniform. We do not want the temperature to vary with time. Ignition delay time might have an activation energy of, say, 40 kilocalories. That means that at, say, 2,000 degrees, 1% error in change in temperature is maybe 20% change in ignition delay time. It kind of goes, delta K over K, the rate coefficient, goes like EA over RT, delta T over T. So that EA over RT, that multiplier of, say, 20 is a big number. So you have to really pay attention to temperature. Even a 1% change in temperature is important, and we can't neglect it anymore. People used to neglect it. So I'm going to show you how we have worked at Stanford over the last 3, 4, 5 years to try to improve the operating range and capabilities of shock tubes. This is a plot of the kind of crude plot of test time versus 1 over T, or here's temperature up here. Roughly speaking, this is where we work with our unmodified shock tube. We can get up to a couple of milliseconds and down to 10 microseconds if we want. We can get up to about a couple of milliseconds at any temperature without any trouble. The rapid compression machine people are up here. They have a more limited temperature range, and they kind of work between maybe 10 milliseconds to 100, maybe a little more depending on their rig. There's this interesting gap here. It happens to be the very gap where the calculated ignition delay time of endodecane, C12, that's for 10 atmospheres, is. That's the most interesting place that we'd like to be. We'd like to overlap with RCMs, and we'd like to get into that regime. Now, this regime is different for different fuels, but this is a motivational slide to show you why we want to do that. So we've modified our shock tube to get access to this range. How do we do it? This is going to look silly, but it works. Here's our regular driver. You want a longer driver because it delays the arrival of the expansion wave. How do you get longer? You have to use lower sound speed or longer driver. We don't have a longer room. So we just turned it around and come back and keep our fingers crossed that that doesn't cause a problem. Or it doesn't cause our biggest problem. And so sure enough, if we use that combination of tailoring, which is mixture, driver gas mixture, and this, we've been out to about 40, 45 milliseconds. It's not perfect, but it's pretty good. And so we can get out into a range where we can make some comparison. Now, I'll show you this. Okay, new problem. When you do this experiment in propane, say 0.8% propane, I think that's equivalence ratio of 0.5. Here's the pressure signal you get at the end wall. Here's the instant shock wave, here's reflected shock. In an ideal world, this pressure is constant. In the real world, it isn't constant. And we call this the dp/dt problem. Is there anybody in here working on shock tubes? A couple people. We call this the dp/dt problem. People used to ignore this problem. Now, in the last 5 years, we're really starting to, it's in the literature now. People will report their dp/dt because you have to do this to model your experiment properly. But the thing is, if this gamma is about 5/3, then if dp/dt is 3% per millisecond, dt/dt is 1.2%. And if you go out here 10 milliseconds, you've just changed the temperature by 12%. You cannot ignore a 12% change in temperature in chemistry. It'll kill you. So, but people have been reporting this number. They report that number for this temperature, the initial temperature. So you can begin to see why, in this regime, different laboratories get different answers, because they have different dp/dt based on diameter and different strategies. We can no longer ignore this problem. People used to be happy with factor of 2 for shock tube chemistry, but we're trying to do much better. So I call this the dp/dt problem, which is really a dt/dt problem. And what can we do about it? You'd like to remove that. Well, we did some work to establish a model so you can calculate what's happening if you report this. But it's more satisfying if we can get rid of it or reduce it. So we built what's called a driver insert. So basically you change the area as a function of distance. And when you do that and you do it right, you get this blue line. These are actually the same initial temperature. So here's what we had before. That little hump is because the driver tailoring isn't perfect. Here's what we get now. Now that's getting a lot better. So when you do that, now the ignition delay time for the same experiment is what? 60% longer? So we were reporting this number. Now we better start reporting this number. That's the right number for somebody who wants to model and model it using the old way of modeling. The way that they model this is by essentially assuming constant pressure and temperature. And the fact is, the experiment was right, but people aren't modeling it right. If you do this experiment, you have to model that experiment. If you do this experiment, people can still use their old-fashioned models, kind of a constant temperature model. But look at the difference in the answer. So it takes a while for everybody to get used to these ideas and decide how to deal with them. Here's the difference that it makes. And it's an evolving thing. We don't have it perfect yet, but we're making advances. Here's what bothered me for a long time. These were the propane ignition delay data from these blue ones were the propane ignition delay data from Wales, someplace in Wales. We're not sure, but we believe the dp/dt was approximately 12% per millisecond. That's because they had a small diameter shock tube. These are our data done the old way, in which we measured our dp/dt and we modeled it. These new data are what happens when we modify our shock tube. So in our shock tube, we go from here to here by changing our design. We're plotting it versus the initial temperature. The same kinetic model should explain all experiments if you deal with this right. So this is the old-fashioned model which applies because we've done the right experiment. This is the same chemistry, but recognizing this dp/dt problem at our magnitude and at theirs. So this is how big this effect is. You know, it's approaching a factor of 10. So you can deal with this by people reporting their dp/dt's and then modeling appropriately. But even better is to try to make the effect a lot smaller. And that's what we're trying to do. Okay. That's an improvement. We call that code ChemShock. Now here's another problem. This is the problem we're working on right now. It's another problem. Most reflective shock modeling assumes constant volume and constant pressure, and you can get away with that if it's highly dilute and you've removed the dp/dt problem, or as you'll see, you can get rid of this problem under certain limits. But the fact is, when you have energy released behind this reflected shock wave and it starts to ignite and release energy, what's happening? It's not constant volume. One boundary is a shock wave. Pressure starts to build up, tells that shock wave to speed up. It's not a constant volume problem. So it's modeled that way, and you can get away with it sometimes up to the time of ignition, but then you're done. You can't model anymore because it is not a constant volume problem. We can see this. Here, I'll give you an example. Here's a heptane experiment. Equivalence ratio of 1 point, that's 4,000 parts per million of heptane, so it's not a lot of heptane. Here's our pressure trace. Here's the pressure change that takes place when we do our experiment. Well, it's obviously not constant pressure. This is the calculation for what the pressure ought to be if it's constant volume. It's obviously not constant volume. So what is it? Somewhere in between. So people have to stop using a constant volume model past here. You might get away with it out to about here. You cannot get away with it afterwards. You'd be okay if there was only 4 ppm of heptane in there, but not at 4,000. And this isn't even air. I mean, this is 4% oxygen. So this is a new problem. This is how do we do a better job of modeling reactive gases in a shock tube problem. So we struggled with this. Well, we developed this code of ChemShock and how we deal with pressure change, but we don't really know what to do with this. I don't know how to specify the pressure. If we use the specified pressure here, if it goes up very much and I force that in my chemistry, it forces it to ignite. And I don't actually want to do that. So that's been a problem which we finally have decided how to solve in the last year or so. So how do you get around this problem? Assuming you've solved the dp/dt problem, now we're just dealing with reactive energy release problem. How do you solve this problem? Use very little fuel. Okay? Now there's a problem. Well, if you don't have very much fuel, how are you ever going to measure the species time histories? There's not enough in there. But you can do that if you apply the method, if you employ the method known as atomic resonance absorption spectroscopy that they use at Argonne. But they can only measure H and kind of O. It's limited. And we'd like to know how to solve this with higher concentrations. So it finally occurred to me there's another way to solve this problem. We can't make it a constant volume problem, but maybe we can get close to a constant pressure problem. I call this the constrained reaction volume idea. We've been working on it maybe a year and a half. We've published 2 papers now. Here's the idea. Here's a conventional shock tube. Fill this, usually use helium driver, unless you're tailored immersive nitrogen. Here's the shock, you fill the shock tube, you fire the shock wave, here's the reflected shock wave. Everything in there is reacting. And that large reaction volume is what gives us the energy release and a change in pressure and hence a change in temperature. Let's constrain the reaction volume. Let's not fill the whole tube. Let's only fill the end. Now, reflected shock comes back, it's processing all this other stuff. All of the reactive stuff is right down here near the end. The amount the number of molecules that can release energy has now been limited by constraining this volume to be small. Now there's difficulties of how you do this, but the point is you can immediately see the pressure change is going to be much less. There's fewer molecules reacting. So that's the idea. Now there's another benefit. When you do these low temperature experiments, sometimes we get funny answers, and when you examine your experiment, you find that it actually starts to burn out here first. It might start burning right there instead of right here. It should burn here first because it was heated first. But if this gas right there happens to be heated hotter, it can burn first. And when it burns, it sends a pressure wave back and affects your pressure measurement, and then you begin to wonder what's happening. Is it igniting here? Why? So that's called the remote ignition problem. So for a long time, people said, why are we getting these strange laboratory to laboratory differences in ignition delay time at low temperatures? The ones that I showed you and explained by dP/dt. Well, I said it's mostly dP/dt. But still, we can find in our laboratory that we still sometimes get ignition out here in certain temperatures. I call that the remote ignition problem. This method avoids remote ignition. There's nothing out there to burn. So all questions about, are you sure you're not bothered by surface reactions, the reaction, all those problems go away with this idea. Now we buy a new problem, but this has got a lot of potential. This is a conventional shock tube experiment with hydrogen, oxygen at 1,000 degrees. Pressure is pretty constant, but not truly constant, so we didn't get rid of the dP/dt there. Bang. Now this is, that's the conventional experiment. I don't know, how do you model that? I don't know how you model it. Here's the new one. Pretty flat. Pretty flat. We still get ignition. It's just that the pressure doesn't change. Why does the pressure not change? It wants to start to burn, sends out pressure waves at the speed of sound, shock wave adjusts itself, and it kind of relieves itself in the axial direction. That's my idea. It works. I think probably you can show that it will work better and better as the tube diameter gets bigger and bigger, but we haven't explored that yet. It works. Now, why do I like this? We can model this. There's no remote ignition. I can now use the first law of thermodynamics for an adiabatic system, and I can say I'm going to use now, instead of constant UV, which is what people have been using, I'm going to use dH as VdP. If the pressure doesn't change, the enthalpy doesn't change, and I now know how, I just do a Chemkin solution for constant enthalpy. That's all of a sudden we know how to do this. It's like a breakthrough. Sometimes in hindsight things look so simple. But anyway, here's another example. This is ethylene ignition. So one of the points is, if you look back, if you're a modeler and you're looking back in history over the ignition delay times, you should favor the more recent data. The old data are more likely to have been plagued by these problems. Point number 2, everybody gets the same answer when the times are less than 1 millisecond. So the facility effects go away. So the data are good for short times. Long times, you have to really pay attention to these problems. People didn't report these issues. So the newer stuff is better. It's not all equal quality. The newer stuff's better. This is an ethylene ignition, 1100 Kelvin, 1 atmosphere, 4,000 parts per million. Now, we always first do the experiment without reaction. First you do experiment without reaction to make sure that you understand the dP/dt problem and fixed it. Then you do the experiment with the reactant. And as long as you don't get very much change, you can model with some confidence that this is either constant P or specified P, and solve through Chemkin. And as a check on this, we did a measurement of temperature versus time, which was not easy. It took a few years to figure this out. How can you measure temperature versus time? So the enthalpy, if the pressure is constant, the enthalpy is constant. But the enthalpy is comprised of 2 terms, sensible enthalpy and the bond energies. When it starts to react, bond energy is changing, temperature has to compensate. So we can measure this, and a measurement of this temperature change is a measure of the change in the sensible enthalpy, which is equal to the change in the bond energy. We've just measured the rate at which the bond energy is changing. Nobody's ever done this before. We're still figuring it out, but I think it's pretty promising. This is what happens with, this is pretty recent. I had the students do butanol ignition delay the old way and the new way. You get a different answer. You better be aware of this. So the modelers have to be aware that there's different ways to do these experiments. But this one we can model all the way through. This way you can model up to the time of ignition, but then you're done. You can't model, because it's not a constant volume process, it's not constant pressure. Now, this reminds me of one more point. We typically plot our time. We measure the time, we plot it at the initial temperature. What do the rapid compression machine people do? They plot their measured time at their peak temperature. Their temperatures decline due to heat transfer. If I don't remove the PDT problem, my temperatures climb. There's no reason why RCM and shock tube data should agree, because they both have opposite problems. Unless the times are short, then maybe the integral of the problem is not so big. So people have to also, so the data are always correct, but you have to model them right. The same kinetics should explain RCMs and shock tubes, but you don't expect the data points to be exactly the same, because they're different experiments. These are different experiments. The same chemistry explains both, but they're not the same experiment. Very important. Yes?
So you're reporting these on an Arrhenius style plot, right? So
Yep.
you still report your experimental data as if it was isothermal?
No, no.
Right, so I'm confused how you select what temperature to report it at then.
The initial temperature. In the shock tube, the virtue is we have a step change in temperature to a number we know to better than 1%. Then things can change, but we know the initial temperature accurately. So typically you measure the time and you plot it at that initial temperature. The initial temperatures, we get a different answer for the same initial temperature because of this effect. Now, what do the rapid compression machine people do? Since that's what you are.
Right.
You're going to take your peak temperature. How do you get it? Well, you get it by some compression model, and you allow for some heat release. You measure the pressure. You kind of calculate it. We calculate it too, but I think we calculate it to maybe 0.5%. But then your pressure goes down, and you calculate the temperature evolution, and you plot your data at your peak temperature. You don't have a zero rise time. You don't have a flat temperature, but that's what you do, and that's okay. All I'm saying is when you plot your point, it's going to be up here. It's going to be somewhere else if you plot it at your peak temperature.
Right.
And in the limit, 10
milliseconds, do you have heat transfer in your system?
No,
also?
no. Big shock tube. This is a problem with the RCM. You should make a big RCM. The heat transfer is on the side. So what you do is you take your pressure record. Pressure goes down. You say it's heat transfer, but your core is okay. It's just kind of isentropic in the core. That's what you do. So this is why I look at the non-reactive pressure trace. If that pressure trace is flat, I'm immune to heat transfer. For us, it sets in our shock tube, it sets in maybe at around 40 milliseconds. So it's a problem, but it's a smaller problem because our diameter is probably 2 or 3 times yours. Because it's just on the edges. So we always have to be, that's a problem, but it's not a problem usually for our time. See, our biggest time here is like 11 milliseconds. If we were to go out to 40, I got to start thinking about this. But how would I check it? I would check the pressure being constant, non-reactive. Because that's kind of telling me what's happening in the core. This is basically what you do. All I'm pointing out is you're going to plot your point, and we shouldn't expect them to agree. The only thing we can expect to agree is the same kinetic model should explain both experiments. Okay, this is my latest thinking. We're almost on time. That's my latest thinking. So it's a little bit of shock tubes and shock waves because we use those together with the laser absorption I'm going to tell you about next. Any last questions before we break?
Do you have different inserts for the driver for different test times, or does it work with all
Yep. Do we have different inserts? Basically what you can show is that you should use a different insert for different temperature regimes. So we have kind of a, that's one of the things we're working on. We're making it easier to change. We'll use the same one maybe over 100 degrees, 150 degrees. It's more of a temperature regime thing. So it's a little awkward. I mean, it's not perfect. We're working on next generation design, but it works. I mean, it clearly explains most of the problems between laboratories for ignition delay time variations at long times. Most of the problems, not all. Then there's this energy release. So it's like I'm telling you about 2 big problems that we've swept under the rug until now. Yes?
How do you do the gas film so that you only have one
Okay.
concentration?
Yes, good question. That's the hardest problem. That's the hardest problem. So we have two strategies. How do we do the gas filling? Okay, that's the trickiest problem. So the ultimate solution, I believe, is what I call a sliding valve, and we're just about ready to try it. Took a year to get this. So we'll have it divided with a sliding valve. But our tubes are 5 inches diameter, so you can't just use a ball valve. Sliding valve. Pressurize both sides equally, open the valve slowly, fire away, make sure you understand acoustic differences. That's the way we need to do it. How have we done it so far so that we can publish some results? We use what I call stage filling. We put the mixture in we want. Then we fill with another inert gas, and we push that interface down the tube. Maybe we shorten the length of the tube by a factor of 10. So we squeeze it down to a smaller region. And we hope that that interface doesn't mix out too fast. Then, because we worry about this and we know we want this to be small, we measure what's happening. So we'll measure with, say, 3.39 hydrocarbons. We'll measure as we fill, and as we fill with the other, we do the stage filling, and we'll see if we end up with the right amount. Or we'll watch it and we'll see how fast it diffuses out. So we do this in terms of what we call L5. What's the final length we're going to end up with? We want it to be 4 centimeters. When we do this, we find we lose about 10% of the fuel or 20% by diffusion. It's actually okay as long as you're close to the end wall and the gas is stagnant. You don't actually care if the gas a little ways away burns at a little different rate. As long as you're monitored, it's like your own little personal reactor. The reactor that's on your laser beam. If you measure the pressure there and you're in the adiabatic limit, that's all. You don't actually care if something happens differently somewhere else. As long as that pressure is constant enough, you don't get to worry too much about effects from elsewhere. So, but to do this then, we've had to kind of develop this scheme that we measure the mixture in place. And it'll usually be a little bit less than what we mixed up in our mixing kit. We mix it up, put it in, and we find that when we push this idea, we start losing 10, 20% of our mixture. It diffuses. It's okay, but now we have to measure it. That's the deficiency. I think when we get to the sliding valve, we'll get rid of that problem. I hope.
So it's only the fuel that you're compressing and then say?
No, you put in a fuel air mixture.
Fuel and air.
Fuel and air and argon, say. 0.4% fuel maybe, stoichiometric argon. Put it in. Now you start filling with, say, keep it simple, fill with argon. Argon goes in, pushing that interface down, 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 and you're compressing, ideally, an interface between two samples of gas. Trouble is they're mixing. And so we fill slowly. We've learned you fill over 5 minutes. And as soon as you're done, you fire it. And you have to measure in place. So we've learned that if we mix it up and put it in, if we push this idea, we might lose 10%. Then maybe when we do it, the incident shock will move the gas, and therefore we'll start sampling a different. Anyway, we track it. That's the hardest part. The concept is right, though. There may be some better way to do this, but the advantage is now, since the pressure is constant or nearly constant, we can model all the way through the combustion. We're no longer limited to ignition. We can monitor the species all the way through. Nobody's ever had this, unless you did an experiment with very little amounts of fuel. You could do the same thing if you fill the shock tube with, 100 parts per million. But if you go to 4,000, you can't do it. Any other questions? Yes?
With the sliding valve, or even the way that you're currently doing it, could you get a reflected shock off the contact surface?
Okay, another good question. So can you get a reflected shock? So for a while we were a little bit naive. We filled it, then we used like pure nitrogen or argon. And then what we observed is that the incident shock was behaving very strangely. And a lot of this, I think, is because we weren't careful enough about there's a reflection off the contact surface from the driver gas, but now there's a new one at the interface of these other, and we didn't pay enough attention to this. So we got some funny behavior. So yeah, you have to pay. So it's like we have to tailor twice. We have to pick a non-reactive gas that looks like the reactive gas, so when the incident shock goes through there, it doesn't do anything crazy. We don't want it to change speed, because it changes speed, it throws off our temperature. So yeah, that's a problem. So these are the two, you guys have mentioned the two things that are hurting us right now. I think we understand them now. Any last question? Okay, we'll break and then come back in 10 or so minutes, 15 maybe.